when we computed the moment of inertia of a homogeneous rod, we actually didn't need double integral. It was just one-dimensional integral. Now let's consider a homogeneous disk with radius capital R and height h, meaning the thickness of the plate. And we want to compute the moment of inertia. So it will be the double integral of r squared dm over the whole disk, where if we introduce the xy coordinate system, then r squared, the distance from the square of the distance from the axis of rotation, assuming it rotates around its circle, around its center. Then r squared is x squared plus y squared of some point, and dm will be the density times dv, and the volume dv will be the thickness times dx times dy. So, and the disk, the set D is the set of all pairs xy from R2 such that x squared plus y squared is less than or equal to r squared, where r is some positive constant, the radius of the disk. So we can write this as the integral of dm is rho dv. We can factor out rho. Oh, okay. Let's start with the general case here. Integral over d r squared, which is x squared plus y squared, times dm, which is rho, which may be a function of x and y, or we can assume the density rho to be a constant, times dv, and dv is h times dx dy. Now, we can compute this in the Cartesian system of coordinates, but it will be easier to go to switch to polar coordinates. So before that, let's write it in the Cartesian system. Rho and h are constants, and if we want to practice the integration in Cartesian coordinates, then we can write it as integral of this expression, x squared plus y squared, dx dy. Then dy runs from minus r to plus r, and then for each fixed y, say this one, x runs from this point, which is minus square root of r squared minus y squared, up to this point, which is plus the same square root, r squared minus y squared. This can be done, but it will be easier in polar coordinates. So rho h are constants, and in polar coordinates we cut it this way. So if we use x is r cosine of alpha, y is r sine of alpha, then x squared plus y squared is r squared. Don't forget to multiply by the absolute value of the Jacobian, which is r for polar coordinates, and dr d alpha. Alpha runs from 0 to 2 pi, one whole term, and r runs from 0 to capital R, from the center to the end of the disk. Well, this will be very easy. First we see that the integration limits are constants and the function splits into two parts, one depending on r alone, which is r cubed, and one depending on alpha alone, which is 1. Integrating 1, the alpha, from 0 to pi gives 2 pi, and this is r cubed. The antiderivative is r to 4 divided by 4 from 0 to capital R, which is capital R to the power of 4 divided by 4. And now times rho h. And now if we realize that pi r square is the area of the disk, pi r square, so we have r2 times pi r, 2 divided by 4 is 1/2, and now we have pi r square, which is the area, times the height is the volume, times rho is the mass of the disk. 1/2 r square m, right? 1/2 r square m. So this is the moment of inertia of homogeneous disk. Well, and to compute the moment of inertia of a homogeneous ball, we can make use of this result because we can cut the ball into thin slices and each slice is a homogeneous disk. In general, for a ball, the moment of inertia would be triple integral of r square rho dv, which is dx, dy, dz over the ball. But if we consider the ball cut into thin slices like that, then this can be computed as integral over z alone, and z goes from minus r to r. This is the center, and now using this right triangle, when this is z and this is r, then the distance from the origin is square root of r squared minus z squared. And we want the square of this distance, so we want r squared minus z squared. This is the integrated function. We can factor out rho in front of the integral, and then we use this result, 1/2 of the square of the radius of the disk times n. So 1/2. This is the square of the radius of the disk. Remember that here r was the radius of the disk, and here r is the radius of the ball, capital R. And this square root is the radius of the disk. Rho is out. M is rho times the volume, and the volume will be height, which is dz, times the area of the disk, which is pi r square, which is this bracket once again. So this bracket times this bracket is this bracket square. We can factor out pi in front of the integral, and we want to integrate this expression. Once again, one bracket comes from r square, and the other bracket comes from mass, which is the density times the volume. And the volume is the area times the height, and the area is pi r squared. And r is this squared. If we explain this multiplication, we have r to 4 minus 2r squared z squared plus z to 4. So the antiderivative is pi rho half, and we can, this is an even function, so we can multiply by 2 and integrate from 0 to r. And the antiderivative is r to 4 minus 2r squared z squared plus z to 4 from 0 to capital R. We have r to 4 in each term. We can factor out r to 4, and we have pi rho r to 4, and then we have 1. Sorry. This is the integrated function. Sorry. And the interderivative, no. The integrated function is r squared minus 2r squared z squared plus z squared. But then, sorry. But then the integrated function is r2. We said, so r is a constant. So we have r squared, r to 4 times z minus 2r squared, and the integral of z squared is z cubed third plus z to the power of 5 divided by 5 from 0 to r this way. Let me check it. Yeah. So we have pi rho, and we can factor out, if z is r, then in each term we have r to 5, so we can factor out r to 5, and when z is 0, this is 0, each term is 0. And then we have 1 minus 2/3 plus 1/5. If we bring these three terms to common denominator, this will be 15, and we have 15 minus 10 plus 3, which is 8 over 15. So we have 8 over 15 pi rho r squared r cubed. I will write r to 5, r squared times r. And then when we remember that the volume of the ball is 4/3 pi r cubed, then if we multiply by 4/3 and by 3/4, then 4/3 pi r cubed is the volume times the density rho is the mass, and this fraction becomes 2/5 r squared times n, which is the mass of the ball. So this is the moment of inertia of a homogeneous ball, written in the form of a double integral and integrated using the result for a homogeneous disk, and then considering all the disks from bottom to top, and then integrated. Actually, this integral is only one dimensional integral.